What if the way we train AI models is secretly biasing them from the start? In most large language models, input and output embeddings share the same weights, a practice called weight tying. It saves parameters, but new research reveals a hidden cost. The shared embedding matrix gets shaped almost entirely by the output layer. Why? Because during early training, gradients from the output prediction task are much stronger than those from the input. This imbalance means the shared matrix evolves to optimize for next token prediction, not for representing input tokens well. We tested this across multiple models. The result? Tied embeddings align much more closely with untied output matrices than with untied input matrices. In fact, the tied matrix looks like an output projection, not an input representation. This mismatch has real consequences. Using the tuned lens technique, we found that early layers in tied models struggle to align with the final output. Their representations are harder to interpret, and they contribute less effectively to the residual stream. Even more telling, when we artificially boosted input gradients during training, the tied embedding matrix shifted toward input-like structure, proving the gradient imbalance is causal, not just correlative. So what does this mean? At scale, the parameter savings from weight tying vanish, but the representational cost remains. That's why modern models like Llama 3 and QN3 untie embeddings for large sizes. For smaller models, where embeddings make up 70% of parameters, tying still makes sense. But now we know the trade-off. You're sacrificing input quality for efficiency. The takeaway: weight tying isn't just about saving space. It's about which representation wins during training. And in tied models, the output always gets the first word.